In this video, let's go ahead and apply our understanding of the distributive property together. So in each of these problems, let's go ahead and see how we can rewrite expressions and maybe think about problems in different ways and still solve them appropriately. So for questions 1 through 4, we're going to go ahead and use the distributive property to rewrite each sum or difference as the product of the GCF and two relatively prime numbers, then evaluate both expressions to confirm that they are equivalent. So what I'm going to go ahead and do here is I'm going to go ahead and use something called the ladder method. I'm going to take this 80 plus 48, and I'm going to go ahead and see if we can find out some common factors here. I'm going to start with 8 because I think that's a pretty common number to choose. We'd be left with 10 plus 6 here, and then 10 and 6 are not relatively prime yet. They have a GCF that's not equal to 1, so I think we could do a common factor of 2. We'd have just left with a 5 plus 3. Now 5 and 3 are relatively prime, so I don't think we can go any further here. All right, so you can see here that our greatest common factor here is going to be 16. So we can go ahead and say that we have 16 here as our GCF multiplied by, and then we have the sum of these relatively prime numbers. The two relatively prime numbers are going to be 5 and 3. Now just going ahead and solving these to make sure they are the same. If you go ahead and solve on the left side here, notice if you go ahead and do 80 plus this 48, that's going to be equal to 128, right? That's if you just kind of evaluate or solve what we originally had there. And the other method is, well, what if we just go ahead and follow the order of operations? If we do that, we're going to do the parentheses first. So 5 plus 3 is going to be 8. So we're going to be left here with what? 16 multiplied by 8 here. And if you go ahead and multiply 16 times 8, see what that's going to be equal to. But 16 times 8 does equal 128, right? So I think if we have the same value on both sides here, I think it's fair to say that we do have equivalent expressions. All right, let's check out number 2 and try this again. Let's see, this time we have 60 minus 45. So hopefully we already kind of know what that is off the top of our heads, just looking at that as its original expression. But if we don't, it's okay. Let's go ahead and give this a try. As a common factor here, I'm going to try to write a 5 out here. We can write 12 minus 9, right? I think 5 is probably the most common number people would think of. And then 12 and 9, I'm going to go with 3 here. And then that's going to be what? 4 minus 3. Okay, so 4 and 3 are relatively prime, so I think we're done here. Our GCF is going to be 15 because 5 times 3 is 15. So we have 15 multiplied by the difference of these two relatively prime numbers, or 4 minus 3. Okay. Now, how do we go ahead and confirm that these are equivalent? Let me see what colors I used earlier. I'll go ahead and use that same green and purple here. So on the left side here, 60 minus 45, that's just going to be 15. So let's plan to get 15 on the right side as well here. So using the order of operations, the parentheses will go first. So it's going to be here, what? 15 multiplied by 4 minus 3 is 1. And then 15 multiplied by 1 is just equal to 15. So if we take a look here, it looks like if we evaluated originally or use the distributive property here, we still get 15 either way. For number 3, we have 39 minus 52. So this is going to be a negative number, right? But let's see what's going on here. They must have something in common, I think. But again, sometimes if you can't, then you would just leave it alone, or the GCF would just be 1. In this case, I think you can divide 39 by 3, and you can divide 52 by 2 twice. I think 13 is a common factor here. So 13 times 3 is 39, and then 13 times 4 is going to be 52. So I think 3 and 4 are relatively prime, so 13 must be the GCF. So if we go ahead and rewrite this using the product of the GCF and two relatively prime numbers, we're going to have 13 multiplied by the quantity of 3 minus 4 here. Now, if we go ahead and just take the difference here of 39 and 52, 39 minus this 52 is just going to be negative 13. Okay. Now, on the right side here, if we go ahead and follow the order of operations, 3 minus 4 is going to be negative 1. So we have 13 multiplied by negative 1. And then 13 times negative 1 is going to be negative 13. So you can see here that either way, we do get the same value of negative 13. And we use the distributive property to verify as well. For number 4, we have a sum here. We have 42 plus 70. Let's see what kind of common factors we can find here. Well, they're both even numbers, but I think they're both divisible by 7, so I'm going to choose a bigger number here. 7 times 6 is 42, and 7 times 10 is 70. As for the 6 and the 10, they can divide them both by 2. We're going to get the sum here of 3 and 5. Now, 3 and 5 are relatively prime now, so we have a GCF of 14. So we can go ahead and say the product of 14, which is the GCF, and these two relatively prime numbers, the sum of them is going to be 3 plus 5. Okay, so let's see if this is true. So 42 plus 70, that's going to be what, 112, I believe. And then if we follow the order of operations here on the right side, 3 plus 5 is going to be 8. So we're going to have 14 multiplied by 8 here. And then 14 multiplied by 8, that's going to be, I think that's going to be 112, right? 112. And so if you see here, these do match. So we're good to go. All right, let's try some different problems here. For numbers 5 through 8, let's go ahead and use the distributive property to rewrite each product as a sum or difference, then evaluate both expressions to confirm that they are equivalent. So notice we do have a product here, like in number 5, we have 5 multiplied by the sum here. So it's a product 5 multiplied by that. Or in number 7 here, we have 6 multiplied by the difference here. So it's 6 times that whole thing. So that's a product as well. So we can go ahead and rewrite these expressions as such. We can just go ahead and take the 5 here. Basically, we're saying there's 5 of these 13. So we can say this is going to be 5 multiplied by 13. Plus, we also have 5 of these 6's over here, 5 times 6. So this would be one way we can kind of get it going and rewrite this as a sum or difference. In this case, we have a sum. And if we go ahead and keep going with this, then this 5 times 13, that's going to be equal to 65. And then this 5 times 6 is going to be 30, right? So this right here would be our sum. Okay. Now, if you kind of keep just going here and then evaluating on the right side here, just because we're almost there, 65 plus 30 is going to be 95. Okay. And then if we go ahead and just use the order of operations for what we had earlier, we have 13 plus 6, use the parentheses first. 13 plus 6 is going to be 19. So we have 5 multiplied by 19. And if you go ahead and multiply 5 times 19, that is going to equal 95. So we can just verify here that both of these do equal 95. And that sum we were looking for was this 5 times 13 plus 5 times 6, which can be simplified to this sum of just 65 plus 30. All right, for number 6, let's try another one here. Let's go ahead and start with taking the fact that we have this 9 on the outside, saying there's 9 of these 12. So we're going to have 9 multiplied by 12. Plus, we also have 9 of these 11s here. So it's going to be 9 multiplied by 11, all right? So this would be a sum here, but this sum can be simplified a bit, right? 9 times 12 is going to be 108. And then this 9 times 11 is going to be 99. If we go ahead and add these two together, let's see. If we add these two together, just to go ahead and evaluate it, this is basically just what, 108 plus 100, which is 208. Then take away 1, that's going to be, I think, 207. Okay. Now let's go ahead and just evaluate the original expression using the order of operations. So parentheses first, 12 plus 11 is going to be 23. So we have 9 multiplied by 23 here on the left side. And then if we just go ahead and multiply this 9 times 23, that is going to be what, 23 times 10, which is 230. But then take away 23, that's going to be 207, right? So it looks like on the left side and the right side, we get 207 either way. For number 7, let's go ahead and take this and rewrite it as a sum or difference. I think this is going to be a difference this time because we're subtracting. So let's say we have 6 of these 11s. So we can say 6 times 11 minus we have 6 of these 4. So 6 times 4. Now 6 times 11 is going to be 66. And then 6 times 4 is going to be 24. So this would be our difference here. All right. Now what if we want to go ahead and evaluate this difference? If we evaluate it, then 66 minus the 24 here is going to be 42. Okay. Now, just to clarify here, this is our difference, and this is our difference that's been simplified. In the last one, this was our sum, but we simplified the sum to get this right over here. Now, evaluating the original expression using the order of operations, 11 minus 4 is going to be 7. So we have 6 multiplied by 7. And then 6 times 7, that is going to be 42. So we have 42 here. And it looks like that matches what we got earlier. So this must be good. For number 8, let's go ahead and say we have 3 of these 9s, and we also have 3 of these 7s. That's what that's really communicating, right? So if we have 3 9s, we can rewrite that as 3 times 9 minus, and then we have 3 of these 7s, so it's 3 times 7. Now 3 times 9 is 27, and 3 times 7 is 21. So this right here would be our sum. Our sum, I guess you can rewrite it as this as a product, the difference of 2 products, but then if you go ahead and simplify it, that's our difference right there. Now if we go ahead and just evaluate it, then 27 minus a 21 here is going to be 6. Now for the original expression, 9 minus 7, that is going to be 2. So we really have 3 multiplied by 2 here. and then 3 multiplied by 2 is just going to be 6. So looks like this also worked out, and we have equivalent expressions here. All right, let's check out numbers 9 through 12. For 9 through 12, we're going to go ahead and rewrite each product using the distributive property to evaluate the expression more efficiently, then evaluate the expression mentally, and check with written work as well. Okay, so let's go ahead and see how we can do this. So 7 times 82, while we could just use standard algorithm, we're not going to do that first. We're going to go ahead and just see how can we break this up a little bit to do it in our head. So I think a good rule of thumb here is to take the single digit here and leave it, and then let's go ahead and break up the double digit into two values that we could find a sum or difference of. In this case, I think because 82 is close to 80, we can say it's 80 plus 2. All right, so in our heads here, we really should be thinking this is 7 times 80, right? And then we're also thinking it's just 7 times 2. Those are two multiplication problems that should be a little bit easier to do. 7 times 80 would be 560, and then 7 times 2 would be 14. So the sum of these would be 576. Okay, so it says then check with written work. So with written work here, you could just also take the 82 and multiply by 7 and go ahead and multiply it out. We're going to get 14, carry the 1. That's going to be 56 plus 1 is 57. So you can see here that we get the same answer either way. But if you didn't have paper pencil, hopefully you could mentally break up 82 into 80 plus 2 and just add 560 plus 14 a little bit faster. All right. Moving on to number 10. This one's very similar because you can see that 42 is kind of like that 82, but again, take that single digit number of 8 and leave it alone here. Let's break the 42, just practice doing this. It's going to be maybe 40 plus 2, that is 42, right? Then we can go ahead and multiply this 8 of these 40s, 8 times 2. I guess in the last one, I forgot to draw these arrows. I think it's kind of nice and helpful to just avoid little mistakes by putting those arrows in here. But really this means what? We have 8 times 40, or 8 of these 40s, plus 8 times 2, or 8 of these 2s, right? So 8 times 40 is going to be 320, and 8 times 2 should be equal to 16. So this should help us avoid using any standard algorithm if we can help it. So this would be 336 for our final answer here, right? Now, what if we just wanted to use standard algorithm just to double check? Well, 42 times 8, that is going to be 16, carry the 1. 32 plus 1 is going to be 33. So looks like we get the same value either way. All right, for number 11, notice this single digit of 6. Go ahead and put that out in front. For 39, that's really close to 40, so I'm going to use a difference here. That hopefully makes sense. This is just 40 minus 1, okay? Now, if we go ahead and distribute here, we have 6 of these 40s, but we also have 6 of these minus 1s here, right? So let's go ahead and rewrite this. It's going to be 6 of these 40s, or 6 times 40, minus 6 times 1. 6 times 40 is going to be 240, and then 6 times 1 is going to be 6. So 240 minus 6 is going to be 234. Okay, so instead of doing standard algorithm, which I'm about to just do just to double check here, you could do 39 times 6. We just basically said we had 46s and we got rid of one after, but 46 is a little bit easier to multiply out. So 9 times 6 is 54, carry the 5. 3 times 6 is 18, plus the 5 is going to be 23. So we do get this 234 either way, right? But you should be checking mentally if you're getting the same values without having to write standard algorithm. For number 12, let's take the single digit of 7 here. 78 is really close to 80, right? So I'm going to say this is 80 minus 2. That's going to be our difference here. And then let's go ahead and evaluate this using the distributive property and see if we can do this without writing any standard algorithm. 7 times 80, there's 7 of these 80s, and then there's 7 of these negative 2s, or minus 7 times 2. So we have 560 minus 14. So 560 minus 14 is going to be 546, I believe. Okay. Now let's check this using standard algorithm. If you take this 78 and multiply it by 7, then 8 times 7 is going to be 56, carry the 5. 7 times 7 is 49, plus the 5 is going to be 54. So looks like either way you do this, you can see we do get 546 both times. All right, let's check out numbers 13 and 14. We'll go ahead and apply our understanding of the distributive property to determine the area of the adjacent rectangles, which just means that they are next to each other in 2 different methods. We're going to sketch and label the rectangles to scale, or the best as we can, and then confirm the areas are equivalent from both methods. Okay, so for number 13, we have a rectangle that has a length of 8 units and a width of 6 plus 11 units. All right, so I'm going to start with just doing the length here. I'm going to do my length on the side. So I'm going to say that this is going to be my length, and I'm going to put this as 8 units. I'm not going to draw it too big, but I'll put 8U for 8 units. And then for the width here, the part of it's going to be 6, so it's got to be shorter than the 8. So just try to roughly to scale here. Draw part of the rectangle. Again, adjacent means they're next to each other, so this is going to be 6U. But then it also has 11 more, so I'm going to go further. And this should be further, I guess fairly significantly longer than the 6, right? A little bit less than double maybe, but as long as it's noticeably longer and it doesn't look too crazily long, that's fine too. So something like this, I think would be fine. So you can see how we have 6 units plus this 11 units for the width here, and then we have a length of 8 units. Okay, and you can see here, if we're going to go ahead and find the area, there's really 2 ways you could do this. If you do them separate, you can go ahead and find the area. So I'll go ahead and write method 1 here, method number 1. So the area here, if we do them separately, we'll have the first rectangle is 8 by 6, and the second rectangle is going to be 8 by 11, right? So this first area is going to be 48 units squared. The second one is going to be 88 units squared. And then 48 plus 88, I believe, is going to be 136. And I think that's going to be units squared here. Okay, so method 1 is really just kind of doing the areas of each rectangle separately. And what about method 2? Well, method 2 is just kind of a different way to kind of wrap our heads around this. So for method 2, we can say the area would be equal to the length here, which is 8, and multiplied by the entire width, though. So not really thinking about this as 2 separate rectangles, but thinking about it as like one giant rectangle, right? So in this case, we're not going to find the area separately. We're kind of saying this is the length, and this entire thing's the width here, right? So if we go ahead and just do this, what we can see here is that with this 6 plus 11, the entire width across here is going to be 17. So we have 8 multiplied by 17. If you multiply 8 times 17, you can go ahead and use the standard algorithm if you would like to, or do it mentally and break it up into 10 plus 7, or however you want to do 20 minus 3 and do a difference. That's fine too. But I know this is going to be 136 units squared. And so you can see the areas are the same here. If you go ahead and distribute this 8 to both of these numbers on the inside, these relatively prime numbers here, 8 happens to be the GCF of 48 and 88. You can hopefully see how these are being written here. You kind of see like the 8 as the common factor here between these two, the sum of these two pieces here, but 8 is a common factor, right? And so the difference here comes to either thinking about these as 2 separate little rectangles, or thinking about this as one giant rectangle here. So hopefully that makes sense. You can find the area both ways because they have a common dimension of 8. All right, last problem here for number 14. We have a rectangle with a length of 15 meters and a width of 9 plus 5 meters. So let's go ahead and see if we can sketch this out here. So let's go ahead and just sketch the rectangles that are adjacent. So they're just gonna be next to each other. I'm gonna call this, going across here, the length, I'm gonna call this 15 meters. And then for the width here, let's have part of it be 9, maybe something along the lines of like this. This looks pretty good. It's definitely not as long as 15, so just make sure it's shorter than that. And I'll call this 9 meters. And then we need 5 more. So again, if we add on, we're just gonna basically put another piece along here, just because we're gonna add the 2 lengths to get the entire dimension there. So we'll just say that's gonna be 9 here. All right, so close enough of a sketch. It's pretty good to scale. Maybe the 15 should be a little longer, but that's okay. As long as they're noticeably different sizes here. All right, so let's go ahead and try our 2 different methods. For method 1, let's go ahead and find the area of each rectangles by themselves again. So the area would go ahead and just be 9 by 15 for the first rectangle. The second rectangle is going to be 5 by 15. If you go ahead and find the area of that larger rectangle, 9 times 15 is going to be 135 units squared, or meters squared in this case. And then 5 times 15 is going to be 75 meters squared. So the total area, if you add these 2 areas together, is going to be 210 meters squared. Okay, now that's one method for finding the area of these rectangles combined. Now, a second method that you could go ahead and do is find the area of the entire thing together. So 15 is the common dimension here, and then we can say the entire width here is going to be 9 plus 5, right? So if you go ahead and do 9 plus 5 here, that's going to be 14. So we can say the area is really just 15 multiplied by 14, right? If you look at it as one big rectangle. Now if you go to multiply 15 and 14 together, you should get that you get 210 meters squared. But if you want to verify that, make sure you just do some standard algorithm multiplication and see if you get that 210 square meters. All right, so in 13 and 14, we're basically looking at some area applications. The distributive property can help you kind of wrap your head around looking at the whole thing as one giant rectangle. If you add up the two smaller pieces for the one dimension, or you can look at them as two smaller rectangles and add the area of the two smaller rectangles to get the total area. So that wraps up this video on 14 different practice problems on just getting a little bit more familiar and fluent with using our concept of distributive property. I hopefully you found the video helpful. If you did, please consider giving the video a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing.